Last time we were looking at prime and composite numbers, and we had gotten to the point, I think, where we're on theorem, are we on theorem 412? No, we're further than that. Example 3? Okay, man, we're even further than I expected. All right, let's take a look. A couple of the theorems at the very end where we were, just as a reminder, we talked about how we can know when we can sort of stop testing to see if numbers are actually divisible and say, yes, we know for sure that they are composite. The way that we made that decision is that we found out that we could actually take the square root of the number as an approximation and know that that's our cap. So this one is our last example last time, 967's approximately 31.1. The smallest prime number smaller than that, the biggest prime number smaller than that would be 31. So we would only need to test up to 31. If we don't find anything before then, we'd know we've got a prime number. We had mentioned last time as well, and it's going to come into play right here real quick, the fundamental theorem of arithmetic. And we talked about how when we break things down into primes, there's really only one way that it gets broken down, except that maybe you want to write it in a different order or something. But otherwise, it's the same set of numbers. They're the prime factors. And so what we're going to do on this example is talk about why that's true. Actually, more specifically, we're going to talk about why 1 is not, and we would not want it to be considered a prime number. So when we talked last time, some of you actually suspected maybe that 1 was a prime number. And the reason that we found out that it wasn't with our definition was because it didn't have two distinct factors. So take a look at this example. It says, show that if 1 were considered a prime number, or prime, every number would have more than one prime factorization. And we're going to do just a very simple composite number. I'm just going to do 15. There's nothing special about it. But I'd like for you to break down 15 into its prime factors, excluding the number 1, because we're going to talk about that part in a minute. What's 15? 3 times 5, you bet. And our fundamental theorem of arithmetic says that this should be unique. There's no other way to do it. Well, here's the problem. If we were to allow 1 to have status as a prime number, we could also have this factorization, right? And all of a sudden now we have 2 factorizations for the number 15. That's not especially nice. It's not especially helpful, but it gets worse. We could also have this factorization. And do you see where I'm going with this? You'd have infinitely many factorizations if 1 were actually considered a prime number. And just from a very practical standpoint, that's not a useful definition status for the number 1 to have. We don't want 1 to be prime because then it ruins a lot of the uniqueness that we have of prime numbers. Does that make sense? Okay. I'm going to do an example with factoring. This is not related specifically to primes, but it is related to Theorem 414. So Theorem 414, just as a reminder, said, whoops, one more back, basically that factors occur in pairs. So if I have a number that divides 24, I'll have the 2 numbers that multiply together to give me 24. They come in a pair, right? So if 3 divides 24, then 24 divided by 3, 8. 8 will also divide 24. They come in pairs. And this is actually an application of that fact. So we have Mr. Arbor, and he wants to plant apple trees in a rectangular array. Okay, we've learned about rectangular arrays. If he has 36 saplings, find all possible numbers of rows if each row is to have the same number of trees. So one option, albeit not a very helpful one for Mr. Arbor, is that we could have 1 row with 36 trees, right? So I'll start us out with that. So we could have 1 row and 36 trees. What else could we have? 2 rows of 18 trees. What else could we have? And I absolutely love it that you guys are going, what I would say, in order, because that means we won't lose something along the way, right? 3 rows of, what was it? 12? 12 trees. What's next? 4 rows of 9 trees. What's next? 6 rows of 6 trees. So it kind of feels a little bit funny when I say they occur in pairs, because obviously 6, 6 is a pair, but it's the same 2 numbers. That's okay. That happens sometimes when we have a perfect square number we're dealing with. We could actually keep going and flip all these around, right? I mean, instead of calling this 2 rows of 18 trees, this could be called 18 rows of 2 trees. So I'm not going to have you write all that down, but just recognize that you could think about it that way if you wanted to think about the number of rows and the number of trees sort of switching locations, and we could talk about those. So these are occurring on all these in pairs. Any questions on that one? Okay. Let's check out our last example in this section. Bob. Bob says that to check whether a number is prime, he just uses the divisibility rules that he knows for 2, 3, 4, 5, 6, 8, and 10. He says if a number is not divisible by these numbers, then it is prime. How do you respond? Any thoughts? What would you say to Bob? He's your 10-year-old in your class and he's making this comment. What you going to say to Bob? Is he right? Is he wrong? Is this a good method? Is it not a good method? What's going on with Bob's thoughts here? It's not right. I agree with you, Brianna. Can you give me some more on that? Why you think it's not right? I mean, these are our numbers that we have tests for, right? I think he listed all of our numbers that we have tests for. Why is that insufficient? Why is that not enough? There are more, what kind of numbers? Whole numbers? Can anybody add to that? Somebody said prime. Does somebody say prime? Thought I heard prime. Can you give me an example of a number that would not divide by any of these? Yeah, Melanie. What's that? 23. Okay, but 23 would be an example of one that kind of fits his pattern. 23 is not going to divide by any of these numbers, and so we could call it prime. And if we tested it by all these and we didn't divide it, we would say it's prime, and it actually is prime. Can you give me an example of something that's not prime? Yeah. 121 is a good example. So why did you choose 121? Okay, so this would be an example. There's one smaller we could use. That's the number 49. It's got the same problem, right? It's not in our list of numbers, and it breaks down into 2 pieces. And if you want to get super creative, you could tell me 77, right? I mean, it doesn't have to be a number squared. I mean, 7 times 11 would also fail this particular argument. So there are other numbers that could divide besides these numbers, right? These are not the only possible divisors. That's the word I was trying to get you guys to say before. They're not the only possible divisors. 7 and 11 are prime numbers that are still, missing from this list. And there are others, right? Because we could talk about 13, or we could talk about 17, or we could even use 23 as an example of a divisor and go from there where Melanie was headed. Okay? So what are we going to say to Bob? Well, we're going to say that there are other numbers we could divide by. So something like this. But what about numbers divisible by, and we can make a list. I mean, 7, 11, 13. I'm just going to put etc. For example, and I'll use the 121 that Brianna gave us. 121 is not divisible by any number in Bob's list. So we're talking about, so it'll say any number in your list. But 121 is 11 times 11. Thus, 121 is composite. Not prime. Does that make sense? We simply have other possible numbers to divide by. All right.